I'm trying to make sure I'm letting people in and reading the PowerPoint both. So hopefully you guys can see the PowerPoint. Welcome this morning. This is the AP Calculus BC content review session. We will be going over Unit 6.12 through 6.14 BC Integration Techniques Part 2. Also Unit 7.5 and 7.9, which is Euler's Method and Logistic Models. So Stephanie Hinz is going to be your presenter today. She is from McCracken County in Paducah, and I'll let her tell you more about herself in just a minute. So some of the things Advanced Kentucky wants to make sure you know is while this is an online review session is intended for a Kentucky audience, space permitting, we welcome students from other areas. We will do all we can to provide every student with an equitable opportunity to learn. During this session, we encourage participation, but please know that any participant causing a disruption to the session will be removed. AP is a trademark registered by the College Board, which is not affiliated with or does not endorse this product. So on the next slide, you'll see are the ways to contact Advanced Kentucky. And then I am Kim Hill. I teach at Madison Central High School in Madison County. And I will be your monitor for today. So I'll be watching the chat and trying to answer questions and letting Stephanie know, just letting Stephanie know if you've got questions for her. So there is my email, kimberly.hill@madison.kyschools.us. And so if you have questions or concerns or just things you need, you're welcome to email me as well, and I can help you as much as I can. And if it's something that we don't know, we have lots of people in our corner that we can put you in contact with. Some meeting etiquette. Make sure your microphones, your video is both turned off, and make sure you are using your chat to communicate. So if you haven't found your chat, make sure you know where that is so that you can chat with us. That's how you will ask questions and let us know if something's wrong. We will be recording today's session, and the place where the recording will be is on the slide that you see at the Advanced Kentucky. So bit.ly/Advanced Kentucky in case you can't see that. So all the handouts and the links and everything for future sessions will be there as well. So thank you for joining us this morning. To getting up on a Saturday, I know it's hard. On the slide that you see currently, there's all the different people and places that you can get help or information that you might need. So Advanced Kentucky, you can email them at advancedkentucky.com. Aaron Timmons is the contact director for Advanced Kentucky. You can also contact him with questions, concerns, or anything you might need help with. Stephanie Hinz is our presenter, and there's her email, and then I'm Kim Hill, and there's my email. Handouts and recordings again is going to be at the bottom link that you see. So there's all the beginning things that I need to let you know about. So I'm going to stop sharing and I'm going to turn it over to Stephanie.
Thank you, Kim. Good morning. This is the first time, not the first time I've presented a review session, but definitely the first time I've presented virtually. So I'm excited to talk with you. I wish I could see you, but I am excited to talk with you. As Kim said, I am from Paducah, Kentucky. So if this is the state of Kentucky, then I'm at the pointy tip at the end. Paducah is about as far west, not quite as far west, but almost as far west as you can go. And so I am interested to know where you are from because I can't see you. So in the chat, I have placed 4 quick questions. What school do you go to? What location is that? I would like to know if you are in-person, hybrid, or virtual, and the last lesson you learned in calculus this week. So I have seen 2 people that have responded, but I'm going to give just a couple of more minutes to do that. And we will get ready for integration techniques part 2. I see that some of you are going to be seeing some of these topics for the first time today. So that's your cue to stop me. If you get something in the chat and you're like, what are you talking about? Please ask me. I would love to help you. So give you just a second to answer those questions and we will get going. This is year 19 for me teaching and which seems crazy impossible for me to believe. But we I've been teaching calculus for many of those 19 years, maybe 1 year that I didn't teach calculus in some format. So we're going to do our best today, and hopefully you'll go away knowing something that you didn't know before you got here. Again, thank you for coming on a Saturday. All right, so I've seen fundamental theorem of calculus. Somebody is at section 610, so I'm assuming that that is like long division completing the square, which is going to be perfect. So for what we do today, fundamental theorem of calculus. Okay, someone's in unit 9, so you're talking about polar and parametrics. That's great. You're ahead of me. And rectilinear motion. Okay, so we're going to be fun. We're going to do great. So here we go. Integration techniques other than substitution. So I'm going to assume that everyone has done a U substitution at this point. And so some of the things that we do will require a U substitution, but we've got a couple other techniques that are specific to BC that we're going to be using. And so a couple of rules that you need to remember. I'm sure you've seen this one before, that the integral of 1 over x dx is natural log absolute value of x, then plus c. So we're going to use that, and that will become important when we're using long or synthetic division to rewrite the integrand. One of the hardest things about integration is knowing where to start. When you're looking at a certain section and you're studying long division, you're like, I got to do long division on every problem. Same thing with completing the square. Well, I need to do completing the square. If it's about improper integrals, I need to use improper integrals. But when you get to the AP exam and you've got all these techniques in your quiver, I like to think of it as like you're an archer and you've got all these techniques. You got to know which one to pull out. Okay. So long or synthetic division, like I said, we're going to try that today. We're going to try completing the square. That's a technique that you learned in one of your algebra sequences, and it does prove important for integration as well. A couple of rules that are going to encounter: 1 over the square root of 1 minus x squared dx. That is arc sine. And these are 2 different forms of the exact same rules. Maybe you learned it this way. Maybe you learned it this way. I have taught them both in different years. Just whichever one strikes me. This one is the easiest, okay? So these are things that you want to memorize. So if you have not yet done that, go for it. All right. So some example problems. We're just going to jump right in. We're going to talk about really the why of why we choose to do a certain technique. So this first one, we've got 1 over 1 plus e to the 2x. Now, my brain always goes to, can I do a U substitution? Because that's the most popular one. And what would be a good U to select? So if I jump in and I look at this problem, I'm thinking, oh, I'm going to pick that denominator. That's going to be great. And then I've got e to the 2x. But if I select that as a u, I'm going to have 1 plus e to the 2x. And if I take the derivative of that, I'm going to have somewhere else in the problem 2e to the 2x, because when you select a u, you're looking for the derivative to be in there at some point too, and it's not. So
can I stop you for just a second?
Sure.
It's hard for me to see. Can you guys say in the chat whether or not you're able to see it? There we go. That's so much better. Thank you.
Yes.
Thank you.
Sorry. Let me try one more thing. This might eliminate some glare too. Maybe not. Okay, well, stop me if you can't. So on this one, I'm thinking we got to try something different. And so I'm going to say, well, maybe we could do, and this is going to be a really strange one to need long division on, but that's what we need. So we've got 1 divided by 1 plus e to the 2x. That's a little bit of a strange situation there. So I need 2 terms there. So I'm going to go ahead and add a 0 in there. Bear with me. And so if we look at just this first term, because that's really all you want to look at, 1 divided by 1. Well, 1 divided by 1 is 1. And since I have 2 terms, I'm going to go ahead and put that 1 right here, and I'm going to multiply. So 1 times 1 is 1. 1 times e to the 2x is e to the 2x. I'm going to do a little subtracting. So 1 minus 1, nothing. 0 minus e to the negative 2x, or to the positive 2x, is negative e to the 2x. And so this is going to be my new integral. I now have the integral of 1, this is my remainder, minus e to the 2x divided by 1 plus e to the 2x dx. So a minute ago, I couldn't see a way to integrate this, but now I have a sum and difference rule, and so I can separate those two, and that's just what I'm going to do. I'm sorry, there's a glare this morning. And so the antiderivative of this 1 dx is easy. So I like to make a rule to go ahead and do all of my integrating at once when I'm ready to do it, because then I don't forget to do a part of it and leave the rest of it. So now the antiderivative of dx is just going to be x. And then this other part. So this is going to be a U substitution. So if I do my U substitution, I haven't left myself a great deal of space here. I've got 1 plus e to the 2x. And so my derivative there is going to be 2e to the 2x. I don't really want the 2 there because I only want an e to the x dx. So I'm going to say 1/2 of du is equal to e to the 2x dx. There's a dx there, you just can't see it. So now I'm going to integrate, and this will be minus 1/2 times the antiderivative of 1 over u du. And I kind of did what I never do. I integrated this part and haven't done this one yet. So I end up with x minus 1/2 the natural log absolute value of this 1 plus e to the 2x and then plus c. And so that is choice letter D, if you look back. All right, so we ended up using long division on this one. All right, and long division is definitely not at the top of my list of things that I'm going to think to use right off the bat. So why did I try long division? Well, I needed to try something, and U substitution didn't work. A lot of times with polynomials, if you have a polynomial divided by a polynomial, then it's in a setup like that, then the numerator and the denominator differ by a power of 1, and that usually the numerator would be up by 1. That's why this one didn't jump out to me immediately as long division. Started with this one, and I'll be honest with you, first time I looked at this question, I started with a different method, and I did not get this right off the bat. I was like, what do I need to try? So I had to try something else, and I say that to encourage you. I've been doing calculus probably close to as long as you've been alive, and I still make mistakes, and you're still going to have to try something. There's this little thing on the end of your pencil. You just cross it out, try again. All right. So long division. Why did I try this? Well, other methods didn't work. A lot of times it's because the numerator is 1 degree higher. Not in this case. All right. So number 2. All right. So looking at number 2. Again, in the hierarchy of the way that my brain works, I'm like, oh, can I use the U substitution? Well, U substitution in the denominator. If I chose that entire denominator, I would have x squared minus 10x plus 34. And that wouldn't work out so great because if I take its derivative, I'm going to need something linear in the problem somewhere. And I don't have that. So got to try something different. So my brain is like, well, maybe I could factor this denominator because we're in BC and we know partial fractions, or some of us have gotten to partial fractions. And so I might think, well, maybe I could factor this and that will come out nice. So 2 numbers that multiply to give me 34 and add to give me 10. I don't think we have any. So this is not factorable in its current setting. So I'm going to try something else called completing the square. And so I saw somebody say that that was the last thing that they learned this week. So let's put that into practice. I'm not going to put you on the spot and call on you or anything. Don't worry about that. So in this denominator, I have x squared minus 10x. I like to leave a blank. And then I've got plus 34. And if I'm going to add something and I want it to stay the same, I better also subtract that same thing. So everybody has their own methods, their own things that they do. I still leave a blank here and leave a blank here for myself so that I remember, yep, got to remember that. Completing the square, you take your b term. You take half of it and then you square it. So 10 divided by 2 is 5. And if we square that, we get 25. 525 here, I'm adding it. I also need to subtract it because you want everything to be an equivalent expression. And now I have forced this into being a nice, pretty little perfect square trinomial. So this is x minus 5. Remember, you take the square root of the x squared, the square root of the 25, and then this will be your sign every time. And then 34 minus 25, that's going to be 9. And so now we're at a crossroads. We're like, well, now what do we do? And this is a rule that we know. We have a 1 divided by something squared plus something squared. These are nice, happy little squares. And so that is going to be an arctangent situation. So arctangent, our a value is going to be 3 because the square root of 9 is 3. And our u value is x minus 5. And I want to double check and make sure that my du is happy, and it is. There is no constant that's involved there. So now, if you know your arctangent rule, which was right up here, my antiderivative of arctangent is 1 over a times arctangent of u divided by a plus c. So here we go. This is 1 over, my a value is 3, times arctan of, then we've got u divided by a. So my u is x minus 5, my a is 3. Then I have plus c. So I'm looking at choice letter C. All right, so why did I use completing the square? Well, U substitution was not an option. And I kind of think about this in a flow chart. I probably should have created a flow chart for you. But U substitution didn't work. So there was no U sub. Couldn't do that. Why else did I choose? There was no partial fraction. I couldn't factor it. It wasn't factorable. So this is not something you're going to find in a book. This is just something that my brain says, okay, how do I go through this? How do I decide? And so since this is not factorable, I tried to make it factorable. How did I know that it was arctangent? Well, I didn't have any square roots in the bottom. Arctangent and arcsine are often the ones that you see when you complete the square, and one has a square root and one does not. Any questions so far? Am I going too fast? Speed okay for you? I'd love to see some comments in the chat if you don't mind. I'm moving on to 3 unless you stop me. All right, so let's look at number 3. All right, so number 3 might be a little bit more along the lines of some of the things you have seen, maybe not. So if you glance at this one, and again, my brain says U substitution first. So when you select a U substitution, hopefully you remember you want to go with a higher power. All right, so if we did that, the higher power is cubic. When we take the derivative of a cubic power, I know everybody in the room you're saying this out loud to your computer, that your derivative is going to end up being quadratic. So I'm looking, do I have anything that's second degree? And I don't. Okay, so that doesn't work out so good. So we got to try something else. Well, I've got a polynomial divided by a polynomial. Kind of stuck, so I probably need to see if I can do some kind of long division, or in this example, I'm going to review something with you. I'm going to try synthetic division first. Synthetic division is when you're dividing by a linear term. And in fact, if you don't like synthetic division, you just go right ahead and do long division. It's going to be fine. You'll get the same answer. So synthetic division. And the reason I'm doing this is I couldn't, there was no U substitution. And if I selected, even if I selected this on the top, I've still got stuff in the bottom, and it's very hard to get rid of anything when you have stuff in the denominator with a du, because you don't want to have that du in your denominator. You want it to be in your numerator. So no U substitution. We've got a polynomial divided by a polynomial. So we're going to try this synthetic division. So I know everybody uses notation just a little bit different. I use a little kind of half box business, and the 0 that's affiliated with this denominator is going to be -5. So the factor is x plus 5, so the 0 would be -5. Then you write your coefficients, keeping in mind that you don't want to skip any powers. So this is 3, that's the third power. 15 is the second power. Then we've got 1, and we've got 9. Synthetic division, you bring down your first one and you multiply. So 3 times -5 is -15. 0 times -5, and add these up. I don't want to insult your intelligence, but I don't want to assume too much, because my BC students, they forget things. So now we are at a point where we can do a little rewrite. So I have divided by a linear term. That means I'm down 1 power from where I began. I'm now at 3x squared plus 0x plus 1, and then plus 4 divided by x plus 5. We have a definite integral, and we're going from 1 to 3. All right, so now we find the antiderivative, and our antiderivative of 3x squared would be x to the third power. We go up a power to 3 and divide, and that's where that 3 went away. The antiderivative of 1 is x, and the antiderivative of 4 divided by x plus 5. This is going to be a natural log. We have our u would be x plus 5. And so if you want to double check that, I don't know how far you are in the scope of doing this in your head. So remember, it would be 1 over u. So the antiderivative will be natural log absolute value of x plus 5. And we're evaluating that from 1 to 3. So for whoever said that you just learned the fundamental theorem of calculus, here's your time to shine. We have fundamental theorem of calculus. I suggest highly go ahead and write your parentheses there so you remember what you're doing. This, if you cube 3, so we got 27 plus 3 plus 4 natural log of 8. I plugged in that 3. Then I'm subtracting. Make sure you have that parentheses there. 1 plus 1 plus 4 times the natural log of 6. And this is 30. This is 2. So 30 minus 2 is 28. And this is 4 natural log of 8 minus 4 natural log of 6. And they are not like terms. And I believe in the answer, they factor out a 4. So if they factor out a -4, actually. And so we would end up with 24. Let's see. That should be a plus. So plus 4 natural log of 8. So we factor out a +4. Sorry about that. Mistake number 1 of 3,000. Then we end up with natural log of 8 minus the natural log of 6. And that is choice letter, what is that, A? Okay. So fundamental theorem of calculus, there you go. All right, let's look at the next one. This is question number 4. Question number 4, this one's not multiple choice, and this is a little bit different. They've given us a differential equation. They said if dy dx equals this, and if y equals 4 when x equals 5, so that's just an ordered pair, what is the value of y when x equals 5.5? All right, so we have 2 pieces of information, and we need to find the third. So this is another really great chance for us to talk about the fundamental theorem of calculus. If you remember in your fundamental theorem of calculus, hopefully, because it's fundamental. So we've got the f of a, or sorry, the antiderivative integral from a to b of f of x dx. We're going to have a situation like this. So they've given us information about the derivative right here, and then they've given us information about an ordered pair. So this is an equation, and we know 2 of those 3 unknowns, so we can find that other unknown. So we know the f of a value, so you can manipulate this and say, well, f of a plus, remember this is just an equation, so this is this situation if we wanted to find the second y value. All right, so if we set this up, and the integration on this one is kind of tough. So we know our starting value. Our starting value at x is 5 is going to be 3. So we know that y of 5.5, that's what we want to find. That's our ultimate goal. And we know this. So we know that when x is 5, y is 3. So that's going to be 3 plus the integral from 5 to what we want, which is 5.5. And then this is our differential equation. So we can write that as 1 divided by the square root of 10x minus x squared minus 24. And it's a differential equation. I did a little separation of variables, and so I moved my dx to the other side. So now we're at a point where we need to decide how to integrate this, because this is about integration techniques. It just allowed me to review a little fundamental theorem of calculus. This is under a radical. So my brain is already thinking, okay, either that entire radicand, that's what's called underneath there, either the entire radicand is going to be a u, or I'm going to have to probably use arc sine. So if I chose that entire thing as my u, I've got 10x minus x squared minus 24. And if I had that, I would need something linear in the problem, and I don't have that. So I'm going to zoom in just a little bit. Maybe you can get a better view of that. I think we're going to need to use some completing the square like we did a minute ago. Let's see how that works. So I've got 1 over. So this is a square root. So underneath that square root, I have, you can change the order of this. I'm going to keep this x, I want that x squared under there. But if you remember from your arc sine has the square root of 1 minus. So I kind of want my constants in the front. By the way, I've looked at this and this doesn't factor so hot. So I don't really have anything that I can multiply to get 24 and add to get 10 so easily. So actually 6 and 4 works in, look at that. So negative 24 plus some blank. Now I'm going to factor this. Well, not I'm going to factor, I'm going to take out a negative. So I've got x squared, and then I would have minus 10x. And so I'm going to have a plus blank here. So if you're thinking, wait a minute, she messed up, I've got a plus here and a plus here. Well, this isn't really a plus because it is got a minus out in the front. So completing my square here, I've got the division is going to be, if I take the 10 and divide it by 2 and square it, get 25. So this is a minus 25. I need a plus 25 here. So now I've got the antiderivative from 5 to 5.5. Then I've got 1 over, and this turns out to be 1 minus, this is a perfect square of x minus 5 quantity squared. And of course I have a dx that I've been leaving off. So this is going to allow me to use the rule for the arc sine. So we end up with 3 plus the arc sine of x minus 5. And my a value, by the way, in this problem would just be 1. So that worked out really nicely. And this is the part that we're going to use the fundamental theorem of calculus on. All right, so this 3 had to be there because that was our initial condition. Plus, now we got to apply the fundamental theorem of calculus. So for you person who just finished that, here's a good review, good reinforcement. So I end up with 3 plus, and then I'm going to do a little subtracting. Remember, arc sine is just looking for the angle that gives a certain value. So arc sine, I've written it this way. I've also written it that looks like the calculator notation, because on the AP exam, they use both interchangeably. So 5.5 minus 5 is 0.5. So we want the arc sine of a half. There I switched in the middle of the problem. And then minus the arc sine of 0. This is the same thing as that. Now we're looking for think about your unit circle knowledge. And so we're trying to decide which angle gives a sine of a half. And so if I did that correctly, that would be pi over 6 gives a sine of half. And 0 is going to give my sine of 0. Or is going to give me a 0 at 0. So my final answer would be 3 plus pi over 6. All right, so I'm going to breathe for a second. How are you guys doing? Gosh, it's so hard not to have the feedback.
It's very quiet in the chat.
Very quiet in the chat. All right.
The only thing, there's one message right now just says it's confusing on where to start, but then once they realize which method to use, it's okay. So you going over how you're thinking is good. Absolutely.
That's what this is all about, is trying to debunk a couple of things. So in the hierarchy of where to go, start with that U substitution. If that U substitution doesn't work, then we're going to come up with ways that we can, if you have a square root in the bottom and it's got a polynomial in it, then you're thinking maybe I need to go to arc sine. So just get your head around some of the techniques that we've got, and then figure out how you're going to get there. And I know that that's hard, because when it's in one section and you're like, oh, well, I do all the problems this way, it's great. These aren't quite so straightforward. All right, so if it's all right with you, we are going to head on into improper integrals. And then my last activity that we'll do will actually help, hopefully, us look through and decide which method is going to be best. So improper integrals, that is in the end of unit 6. It's long about 612. So some of you may have seen this, some of you may not have, but that's okay. We will be fine. All right, so improper integrals. You are using these on a definite integral that has either or both the limits of integration be infinite, or if you have a discontinuity at one or more points within going from A to B. So you are, and sometimes these are very obvious. If they have an infinity for A or B, then you're like, oh yeah, that's improper integrals, bingo. The ones that are sneaky is when you have some type of an asymptote, some kind of discontinuity within the A and B. And so we'll encounter one of those as well. You are going to use a limit, everyone's favorite, to rewrite and, quote, remove this issue with infinity or with the discontinuity. And if you haven't seen these words yet, I promise you will. Unit 10, it's all over it. But if something is going to converge, your improper integral is going to converge if the limit exists, and it will converge to that point. And if you get a situation that fails to exist, you're going to answer with this integral diverges. All right, so let's hop right in and see how this goes. And each one of these, still we're talking about the different methods, but let me see if I want to do all of these. Let's actually skip to number 6. And if you can zoom in a little bit more again, where there's so many words, it's hard to see again. So that's good, like that. Very good. Thank you. All right, so if we're looking at this problem, this is one of those sneaky ones because we don't have infinity here or here. And those are the ones that scream improper integrals. However, if we look at this problem, number 6, 1 over x squared, this x squared should get your attention. And it should get your attention in the fact that 0 is a problem. 0 is going to be an asymptote. So from -1 to 0, or -1 to 1, we're definitely going to have a situation where we've got 0. So the way that you rewrite this is you're going to go from -1 to 0, and we're going to throw a, let me give myself a little more space here. We're going to throw a limit out in the front. So the limit as b approaches 0 from the left, and we're going to go from -1 to b of x to the -2, just rewriting that a little bit to make it easier, dx, plus, so basically I'm using a little I call it the pit stop property. I don't think it says that in the book, but if we know that 0 is the problem, we can go from -1 to 0, which in this case is going to be b, and then we can pick right back up, and we're going to say going from the limit as a approaches 0 from the right of a to 1, and this is x to the -2 dx. So this is my pit stop property. In this case, we've got 0 from the left, we've got 0 from the right. If it's on the bottom, I typically use A. If it's on the top, I typically use B. However, if you like a different letter, you can use a different letter. Just don't use X because you don't want this to be the same as that, okay? So now we try and integrate this, and this is a nice, happy little thing to integrate because we don't have to use any fancy techniques. This is just a power rule. So I have the limit as b approaches 0 from the left. This is x to the -2. So that becomes -x to the -1. And we're evaluating that from -1 to b, plus, then we're going to do the limit as a approaches 0 from the right. Same deal, -x to the -1, and we're going from a to 1. Okay, my person who just learned fundamental theorem of calculus, we get to do it again. We're practicing fundamental theorem of calculus here. And I make it a habit to go ahead and do one of these, because if one of these diverges, then the other one it doesn't matter, okay? So let's try this one first. We've got, and I don't like negative signs, so I'm going to put this negative out in the front. I've got negative, and then I have the limit as b approaches 0 from the left. I've got 1 over b minus 1 over -1. And so now I like I said, I'm not going to go with this one just yet, because if this one diverges, so we'll see what happens. If I plug 0 into this, I've got 1 over 0. You got major light bulbs going off and saying, I can't have that. 0 can't be on the bottom. So 1 divided by 0 doesn't exist. This limit doesn't exist. So therefore, this integral diverges. Okay, great. Now we got to do a little reading. So I know that it's not A. I know it's not B. This integral diverges because the limit as x approaches 0 from the left of 1 over x squared doesn't exist. Well, that's not what we found out. We found out that the limit as b approaches 0 from the left of 1 over b, that's where the problem was. So our answer is choice D. So this was improper integrals. And why? Well, our why was because we had a discontinuity within A to B. All right, number 7 is a super difficult one. We're going to come back to that. Let's go to 8 for just a moment. Let's go to 8. All right. So hopefully you found that one. And you see this is definite. And you see that there's an infinity in there. And so for you, whoever commented and said, I don't really know where to start, this is one that says, hey, breathe easy, you start here. And this is an improper integral. Why is this an improper integral? Well, we have infinity as a limit of integration. So if we have infinity as a limit of integration, we can rewrite this. All right, so this is the top one that has the issue. So it's my habit, because I usually use b on the top. I say the limit as b approaches infinity of the integral from 1 to b of x e to the negative x squared dx. Now, I don't really say approaches infinity from the left or the right, because you can only approach infinity in one way. I use the left and right when it's something in the middle, or if it's a definite value. Infinity is not, so we can only approach infinity from the left anyway. So now we're at a situation where we want to be very careful, because we don't want to alter our limits of integration. So in my mind, I'm thinking, if I have a u, and the u is the exponent right here, if I have a u, and that would be negative x squared, then my du would be negative 2x dx. And if you'll notice, I don't need that 2. I don't need it, so I'm going to divide by it. And I know everybody does U substitution just a little bit different, but I like to think of it as a puzzle. So this is e to the u, and I know that x dx equals negative 1/2 of du. So I've got negative 1/2, the limit as b approaches infinity. And so this is e to the u, and the antiderivative of e to the u is just e to the u. So again, I am not writing u in this problem. And the reason I'm not is because when you change to u, then technically your limits of integration should change. So I never, when I'm doing an improper integral, I might use a U substitution just to help me think, but I keep it into my dx values. I'm going from 1 to b. So I now have negative 1/2 in the front, and I've got limit as b approaches infinity. And so this fundamental theorem of calculus, whoever said that, you're getting a workout today. E to the negative b squared minus e to the negative 1. Okay, when you plug that in, remember this is not negative 1 quantity squared, it is the opposite of 1 squared. And I still have BC students that mess up on that all the time. Heck, I mess up on it too. So now I want to plug in infinity. So this gets a little bit complicated. We really need to think about this. I have negative 1/2. And then I have, this is 1 over e to the infinity squared minus 1 over e. Well, infinity squared is infinity. And 1 over infinity is 0. Remember that from your first unit, I hope. When you divide by a gigantic number, then that's going to end up being 0. So we end up with negative 1/2. This is 0 minus 1 over e. So let me scoot over my fancy technology. We've got 1 over 2e. I think that this is an extremely reasonable question that you could see on your AP exam, because this test, do you know improper integrals? Absolutely. Can you divide by infinity in your brain? And remember that the power is much higher here, so that's 0. Can you do the fundamental theorem of calculus? There's so much in this question. So 1 over 2e is going to be our answer, and that is letter B. All right, so We're at 9:45. I probably got time for one more question. 7 is quite difficult. I would like to look with you, let's see how our time goes, but let's look at 9. I always have too many problems. All right, so 9 is going to remind you.
Stephanie, can I stop you? There's a question. Will you use any points if you change to u and then forget to change the limits of integration, but then you sub x back in?
If you sub the x back in, I think that they will overlook that intermediate step as long as you go back to the right things. If I were you though, just to be careful, if you use a u, then leave out your limits of integration. Do the U substitution out by the side without the limits of integration. Just do it as an indefinite integral. And then once you have your answer, then I would put it back in and change it back to definite. Does that make sense to you, Miss Emily? I think that might clear that up. All right. So if she follows up with that, stop me, Miss Kim. All right, so
she just says, what about writing u of b temporarily? I've never seen that myself, but
I haven't either. I don't know. I can ask and I can get back to you. If you're interested, follow up with an email with me and I will find out the answer. I just don't know off the cuff what they would do. I would highly consider doing indefinite out to the side with your u and then coming back and using your limits of integration, because I always want my students to have matching limits of integration, the integrand, and the letter with the differential, the dx, the du. I want those 3 things to match. And I would have to ask somebody much more intelligent than me about the specifics of that. So thanks. All right, so consider the function f given by this for all x greater than or equal to 0. Evaluate the integral from 0 to infinity of f of x dx, or show that the integral diverges. All right, so this will be the last one of these that we try. And if you're looking at this, I hope you realize, oh, that needs improper integrals. Because we have an integral, we have an infinity in the limits of integration. One other thing that I hope catches your attention is that we have 2 things multiplied together. And if I used my u to be 2x in the numerator, in the exponent, if I use that to be my u, then I got to deal with this x here, and that doesn't work out so great. So when you have 2 things multiplied together and you have integration, we don't have a product rule, but we have something called integration by parts. And Ms. Hill did that the last time we had a session, but I thought we'd throw one in just for review. So you're going to have a setup like this. You've got the limit as b goes to infinity of the integral x e to the negative 2x, and we're going from 0 to b. So if you will remember, when we have u and our dv, so everybody does this a little bit different as well. I have seen in multiple places the acronym LIATE. So this is a suggestion on how you select your u. So try to pick a log. Try to maybe pick an inverse trig. A is going to be some type of an algebra situation, trig, and then exponential last. So I'm going to pick I'm going to pick just the x, excuse me. So then my du would be dx. And so the rest of the problem, I would be selecting e to the negative 2x. So my v in this case would end up being negative 1/2 e to the negative 2x. So this was, remember, the antiderivative of e to the u is e to the u, but you have to account for the fact that we have a negative 2x. So the derivative of that is negative 2, and it ends up being in the front. So now, integration by parts is what we're also adding in here. So integration by parts is u times v. So my u is x times v, and my v is going to be negative 1/2 e to the negative 2x. And I'm evaluating that from 0 to b. And out here in the front, I still have a limit. Still have a limit out in the front. Minus, then we've got the integral of v du. So my v value is negative 1/2. And I've got e to the negative 2x. And then my u dv is going to be just my d. I have a mistake over here. I said x and then I said dv. That should be my dx. So now this is what I'm going to be integrating. And again, I'm still going from 0 to b. So this part is ready for a little fundamental theorem of calculus action. This part's not. So I'm going to do it all at once. Still have a limit in the front. The antiderivative of e to the negative 2x is going to be itself divided by the derivative of negative 2x, which is going to be negative 2. So that's going to make this negative 1/4. And we're going to be evaluating that from 0 to b. I'm going to use my fundamental theorem of calculus here and here. And I'm going to remember that I'm plugging in infinity for b. So if I plug in infinity for b, I've got negative 1/2 times infinity, and then divided by e to the negative. So we've got a whole lot going on there. Let's just plug that in and look at it. And then if I plug in 0 here, thankful to this x, it makes the whole thing 0, so I shall leave that alone. Minus, I've got 1/4. We're going to get there eventually. And so this is going to be e to the negative 2b. And then this is minus, I've got minus 1, the 1/4 is in the front, and then I've got e to the 0. All right. So this is a difficult problem. When we look at this, I've got infinity in the top, and I've got e to the negative 2b. So that means that this whole part of the term is going to go to the denominator. So if I write it like this, I've got negative b in the top, and then I've got 2e to the 2b. I'm just going to leave the rest of this alone. I know you're like, let's just finish the problem, Hinz. But I think it's important for us to look at this part right here. All right, so when we plug infinity in there, do you remember when we talked about, and you can look at this in two different ways. You can look at it within the idea of the magnitude of the function. You can also use L'Hopital's in this situation. However, the magnitude of this denominator is much larger. E raised to an infinite power is much larger than just infinity. So the numerator loses in this case. The denominator is our winner. And if we're dividing by a much larger value, that's going to end up just being 0. So this is 0. Negative 1/4, this is also 0. Negative 1/4 times negative 1, this is 1/4. And that, my friends, is what I would call a bust your chops kind of problem. What did we talk about in this problem? Well, just about the whole the whole course. We talked about improper integrals. We talked about the fundamental theorem of calculus. We talked about limits. We talked about L'Hopital's. We talked about magnitude of functions. Oh my goodness, this was a toughie, okay? So it is 9:55. I have a little bit more in this section, and then I will move on I will move on to Euler's method and logistics. So if you'll take maybe a 5 to 8 minute break, and then we'll come right back in here. Please put any questions or suggestions you might have in the chat. Yes, I will. All right, I think I'm going to start back here. Mrs. Kim, are we ready? Anything from you?
I think we're ready to go when you're ready.
All right, so I do want to, I always have too many problems, and I don't want you to not have some guidance on them. So I will tell you on number 5, if you are interested in seeing a detailed explanation, I can certainly share that. I could share that with Aaron, and maybe he could post that. I also would be happy to respond to you on an individual basis if you tried it, and maybe I could give you some feedback. My email is on the front of this, and I'd be thrilled to help you out if you're interested. Number 5, I can't really give you the answer because it's just one of those show that this is true situation. And I did skip that one because I wanted to work some problems because I know some of us did not quite get to improper integrals yet. And I wanted you to see just some problems worked out. Again, I know that I have to go quick through some of the things that some of you have never even seen. But again, if you have any questions, holler at me. I will tell you I did not get to question number 7. If you would like to work it and try to get the answer, you will get C as a correct answer. So if you would like to see that worked out, again, a quick email to me, and I'll be glad to do that with you. On the back, this is not quite the back of the packet, but I do have a little activity that I want us to talk through before we get started with my second session. And this goes back to what comment, I had a comment about confusing where to start. So maybe this will help us recognize some of the differences. So in this technique or this activity, it says select the best technique for each problem. The choices are listed below. Indicate your reasoning and use each technique only once. So we're not actually going to integrate these, although I do have the answers to all of them if anybody wants to check with me as well. So number 1, we've got 1 over x squared plus 2x minus 3. So my brain always goes to U substitution. You might want to start with U substitution and try to find the one that you want, but I want to get quick recognition. This is not a good choice for you because my denominator would be a good choice for would be a choice for my U. But if I take its derivative, it doesn't appear anywhere in the problem. So U substitution is off the table. So this denominator could possibly be factored. Let's see if we can. We've got an x and an x, a 3 and a 1, and I would need this to be positive and this to be negative. So if you have seen this technique already, fantastic. I know that Ms. Hill did a great job on this last unit, but this is a candidate when something factors really nicely for partial fractions. So partial fractions, that is choice letter C. And why could I do that? Because I could easily factor the denominator. Not fact on. Sounds like a new superhero. The fact on. So factor the denominator. Choice C. The next one. So if you look at, let's see if we can get a little bigger here. Y'all are gonna be seasick watching my screen change. So if I look at this, like, okay, this is looking good. I've got a higher power in the denominator. Maybe I could select that entire denominator. That entire denominator would be x squared plus 2x minus 3. So my du, my derivative would be 2x plus 2 dx. Now my AB students might be kind of frustrated because they're like, oh, that's not exactly what we have in the top. But hopefully you as a BC student quickly say, oh, well, I've almost got that. All I need to do is divide it by 2. So if I divide that by 2, I have the perfect U substitution. So this is A. Why did we pick that? Well, we picked that because when you take the derivative, okay, so you select the U, no, you don't subtract the du, you select the U, and du is in the numerator. and I selected the u from the denominator. That's how it happens so often. If you have a numerator and a denominator, I can't think of an example. There might be one, but I can't think of an example where you would select the numerator and then the denominator is automatically there, unless it was a very specific situation. Maybe you had a natural, if you had a natural log in the numerator, if you took that denominator or that as your u, then that might potentially work. But if you just have a polynomial in the numerator and the denominator, you would select the u from your denominator. Okay, the next one. Number 3. So number 3, we've got x squared plus 2x plus 3. Okay, so a novice calculus student might say exactly what I just told you not to do. If you selected the numerator as your u because it's the higher power, then we actually have the same u as what we had in the previous problem. The problem here is when you found your du, it would be in the denominator, and you can't have that. So your du would not work for this problem. So because our higher power is in the numerator and it differs by only 1, I'm kind of inclined to think that long division is an option, and this is what you need for this problem. And the reason being is because if you selected the u, it would have to come from the numerator, and you cannot do that. All right. And so our B is, if you select the u from the numerator, the du can't go in the denominator. So we also have a very simple candidate for not implicit, for synthetic division. That word didn't want to come to my head. Anytime you have a polynomial divided by a polynomial, if U substitution doesn't work out, then it's a really great candidate for long division, or in this case, synthetic division. You can only use that when you have a linear constant term there. I said linear constant, that sounded kind of strange. When you have a linear term in your denominator. Number 4. So number 4, if you glance at that one, again, we're using basically a polynomial on the bottom. So if you picked your u, your du isn't anywhere in the problem. So that's not going to be a good candidate for U substitution. And by the way, we've already used it, and we can't use it more than once. So we've used C, and we've used A, and we've used D. On this one, I think because I can't factor this bottom, this is not factorable. And when something is not factorable, then a good option is to complete the square. So if I complete the square, I do not have a square root. So this one is going to look like arctangent, and that's going to be choice letter E. So if I complete the square, and you notice there is no square root, so that's what's going to make it be tangent as opposed to arcsine. Arctangent instead of arcsine. Number 5, okay, it's definite. And upon first glance, this doesn't look too bad. However, if I factor that denominator, I've got x plus 3, and I've got x minus 1, then I have a problem when x is 1 and a problem when x is negative 3. Well, x is negative 3 is not an issue because that's outside of this interval. However, because x equals 1 is inside the closed interval from A to B, this is an improper integral. And this would be an extremely easy one to miss as improper if you're not careful. So watch yourself on this one. This is an improper integral. That is choice F. Why? Because an endpoint or a limit of integration is an asymptote in this function. Oops, you can't see that, I'm sorry. All right, so looking at this next one. This one catches my eye because it has a square root in the denominator. When I see a square root in the denominator, my brain is thinking, okay, either this is a U substitution or it's going to be an arc sine situation. And this one couldn't be a U substitution because this is quadratic and I would need a linear term somewhere else in the problem. I don't have that. So this is going to be something that I have to use completing the square. And I have a square root in the bottom. Remember, my U substitution didn't work, so we are selecting G as our option for that one. And number 7, we have one left, but this one honestly should be the most obvious one to you if you've done this unit yet. This is what Ms. Hill taught in her session in January. But if you've not gotten to this, it's going to be something that you're going to rock because it's something that once you've seen a few, they're pretty much very straightforward. We have multiplication. If this were a derivative, your brain is thinking, I need the product rule. And if your brain thinks, oh, I need the product rule, then in integration, about 98% of the time, you need integration by parts. Now, let me say that if this had happened to be 1 power down, if this instead of x squared plus 2x, maybe you had 2x plus 2 right here, then it would have been a U substitution. But if you take the derivative of this, you're not going to get this guy. And if you take the derivative of this, you're not going to get this guy. So this is integration by parts. And it's because it looks like a product and neither is the derivative of the other one. Okay. All right, so I'm going to move forward from this section. If you'll notice, there is a reference page. The back 2 pages are just some things that you might want to put on your radar as things you want to make sure that you memorize. If you have any questions about integration techniques, please holler at me. My email is at the front of that. But I'm going to move forward and look at Euler's method and logistic models. Unfortunately, we probably won't get to every problem, but I expect that every time I teach, even in my classroom every day. My students would totally agree with that. I saw one of them this morning when I went through the Chick-fil-A drive-thru. All right, so Euler's method. This was developed by Mr. Euler, and we often hear people say it Euler, which reminds me of Bueller from the movie, and it kind of makes me think of, you guys are too young to have watched that movie probably, but the teacher stands up there and says, Bueller, Bueller, and nobody answers. That's kind of the way I feel today because I can't hear your sweet voices. All right, so Euler's method. This is a very simple numerical approximation technique. If you can write a tangent value, a tangent line, then you can do Euler's method, okay? It's just writing tangent lines and substitution, that's it, all right? We need to know a couple of things. Our delta x is going to represent a change in x, which is going to be our step size, and it's going to be calculated by b minus a over n. You're going to encounter this multiple times if you haven't already. End point minus starting point divided by the number of changes, so the number of steps. So some things you want to recall would mean you would want to know about your tangent line, and you want to use point slope form. Slope intercept is overrated. So point slope, y minus, you plug in for y1, you plug in for m, and you plug in for x1. If you alter this just a little bit, a tangent line approximation is going to be y is approximately y sub 1 plus m times x minus x1. Now, put in calculus terms, remember our m is going to be our dy dx. That is just going to be Leibniz notation for a derivative. And this x minus x1 in this situation is a change in x. It is a change in x. All right, one thing I want to remind you of, when you have a tangent line, this is the tangent line, this is our function. When this function is concave down, the tangent line approximations are going to be an overestimate. Although we will not encounter those in the questions that I have prepared for us today, I have seen multiple questions where it asks about overestimates and underestimates. And when you're using a tangent line, it has to do with the concavity. So the converse here, if we have tangent line on a concave up function, if you'll notice, if this is the point that you calculate your tangent line, then if you use that to calculate what the value is right here, that tangent line is going to be a smidge lower than our function. So that will be an underestimate. So let's jump in. I'm going to show you the way that I do this. Some people use a chart, some people use tangent lines. I tend to use a chart most of the time. So here we go. Let's see if we can jump through this. Consider this differential equation. That's just a slope. Let y equal f of x be a particular solution to the differential equation with the initial condition that. Okay, so my students get excited. They see a particular solution. They're like, oh, I need to find it. No, it doesn't say find it. Look for the verb. It says let it be a particular solution. That doesn't mean go find it. And so we're going to use this initial condition. Use Euler's method with two steps of equal size starting at x equals -1 to approximate f of 0. Okay, so this is a repeated approximation technique. All we're going to do is we're going to start out with some x value. All right, and I do use a table to do this. So we're going to start out at the value -1, 2. So in the first step, right there, I'm going to leave myself a little bit of space because our approximation is always going to be a previous y. So the previous y plus your slope times your change in x. That's what we just talked about a minute ago. Your previous y plus your slope times your change in x. And then I'm going to leave a column over here for our slope, which is our derivative. And in this case, it is 6x squared minus x squared times y. All right, so I need to know what my step size is. So that means I need to know my goal. I'm starting at -1. I'm ending at 0. So my delta x, my change in x, will be ending point 0, starting point -1. And they told me I want 2 steps. So 0 minus -1 is 1 divided by 2. So my step size is 1/2. I like to set up my chart. So this is -1. If I add my step size, -1 plus 1/2 is -1/2. And then -1/2 plus 1/2 is 0. And that's going to be my goal. So I know that when I get to right there, that's going to be my answer because I want to approximate f of 0. So here we go. Table's set up. Now it's just a calculation situation. So my ordered pair, -1, 2, I'm going to plug into my slope. So 6 times -1 squared minus -1 squared times 2. So you have to do a little arithmetic in here, which on the AP exam, you don't have to do very much arithmetic. You can leave your arithmetic, but this is a situation where you got to do it. So this is 1 times 6. 6 minus, I think I forgot a square, didn't I? So this is going to end up being 6 minus 2, which is 4. This is my new slope. So over here, I have the previous y, okay, 2 plus my slope, I just found it, is 4. And my delta x for this problem is always a half. So 2 plus 4 times a half, that's going to end up being 4. All right, guys, this is a new ordered pair. -1/2, 4. I'm going to take my new ordered pair, -1/2, 4, and I'm going to plug it into and find my new slope. So my new slope is 6 times my x value, which is -1/2 squared, minus -1/2 squared times 4. So that's going to require me to do even more arithmetic. This is 6/4, and this ends up being 1. So 6/4 minus 1 is 6/4 minus 4/4, which is 2/4, or just 1/2. Yes, that is arithmetic that we could expect you to do. So now that's my new slope. I'm done with this first line. Once you use a line, you're done with it. Move on. So here we go. We're done. We've completed this line, and we're going to use it. So this is going to be my previous y. Well, my previous y is 4, plus my previous slope, which I just found, which was 1/2, times my step size, which is 1/2 for this whole problem. So 4 plus 1/4 is going to be 16/4 plus 1/4, which is 17/4. So there's my answer. All right, I like this next problem because it is set up in a table. Maybe you didn't get all that. Let me give you a second. My students are always like, slow down. You're probably saying the same thing. All right, so question number 2 has a table. So it says, assume that f and f prime, notice in this one, f prime comes first, which is strange, usually f does. Assume that f and f prime have the values given in the table. Use Euler's method with 2 equal step sizes to approximate the value of f of 4.4. And believe it or not, this is still, even though we have decimals in here, this one is still marked as a non-calculator style question. So let's try it. We have one ordered pair here. Our ordered pair is 2, 4. So I'm actually going to start there. That's the only one I have. It's my only choice. So 2, 4. Now the next thing that you need to do is find the slope. So f prime of x. So our x value is 2. So here I'm looking for f prime of 2. And they didn't give me the function, but they did give me a table. So f prime of, hold on just one second. So f prime of, I got that backwards, don't I? My ordered pair is not 2, 4. My ordered pair is 4, 2. Let's try that again. That was not going to work out so great. So now, f prime of 4 is in my table. So f prime of 4 is -0.5. So now I got to figure out where I'm going. I'm going to 4.4, and I want 2 equal steps. So 4.4 is my ending point. My starting point was 4, and I want 2 equal steps. This is 4.4 minus 4, so that's 0.4 divided by 2, which is 0.2. So this is my delta x. So that means I'm going to add 0.2 to 4, and then I'm going to do it again. And when I get to this point right here, I'm going to stop. I'm looking for whatever I find right here. So now, writing a tangent line. Our tangent line is always the previous y plus my previous slope times my step size. So my previous slope was -0.5. I just wrote -0.5. -0.5 times 0.2 is -0.1. So 2 minus 0.1 is 1.9. I didn't leave myself much space, did I? And so now this looks like it might be a little more difficult, but it's not. In fact, I don't have to calculate it. I just look at my table. I want to find f prime of 4.2. Then I look at my table, f prime 4.2. So I've got negative 0.3. All right, ready for a new tangent line. Remember, it's previous y plus delta x times the previous slope. So previous y is 1.9 plus my previous slope, which is negative 0.3, and my step size, which is 0.2. So this looks almost impossible, but I promise it's not. This is 1.9 minus 0.06. I thought the arithmetic was harder than anything in this problem. So they might have given you a calculator on this. I think I might have. So 0.9, I got to do a little borrowing there, and I end up with 1.84 as my answer. I love that question because that, you know, in each one of these topics, they look at, there's a glare. Hold on, let me see if I can move. I need to quit moving there. In every one of these questions, they want you to look at this in terms of a graphical perspective, in terms of a tabular perspective, and then just analytical. And this is a great example of a tabular problem for Euler's method. Anything in the chat? Any questions so far? I do want to watch my time.
I have asked if you could go back up to the work for question number 1.
Absolutely. I told you I went too fast. That's the way I roll. Feel free to take pictures of the screen if you want to do that, and then you can go back to that as well. I'm going to skip number 3 for now. I'm going to let you work that problem on your own. And 3 is going to give you the answer D. So I want you to go ahead and mark that. And while you're doing something this afternoon, work one calculus problem and see if you can't get D as an answer. I'm going to go to number 4. I'm assuming we've probably had enough time now. Here we go. So number 3, like I said, is D. I want you to see if you can work it. It does not vary from either of the previous 2 problems. I'm selecting number 4 because there is a bit of a change on this one. Tiny change, but important change nonetheless. It says let f of x be the particular solution to the DE. Notice it didn't say find particular solution, so you're not gonna, my students forget to read the whole question. I know none of you would do that. With the initial condition 0, 1. Use Euler's method starting at 0 with 2 steps of equal size to approximate negative 0.6. So do you notice what's different about this problem? Our starting point is at 0 and our ending point is at negative 0.6. Everything that we've done up until this point, we've started at a value and we've approximated something larger. This one we're approximating something smaller. Not a big deal. We're just going to have a negative sign in a strategic place. So we want to find our delta x. So our ending point is negative 0.6. Our starting point is 0. We want 2 steps of equal size. So this time our delta x is negative 0.3. Okay, and that's a change because before we always had a positive delta x. And so when we set up our chart, we started with our x value and we added that delta x each time. We're going to subtract this time. So our x value, our beginning spot is at 0. Our y value is at 1. I'm leaving space. And so then we want to do our dy dx. And I will normally just go ahead and write that in. This is a non-calculator question. So you're going to take X and your Y value, and you're going to plug that in. You've got 1 plus 2 times 1, and 1 plus 2 times 1 is, now you're going to have 0 times 2 times 1 plus 2 times 1 is going to end up being 2. All right, so now my delta X, that's going to be what controls is here and here. I want 2 steps, and I want to get to negative 0.6. So going from 0 down 0.3 is going to be negative 0.3. And then if you do it again, we're going to be at negative 0.6, and that's my goal. So this is going to be my stopping point when I get right here. So this is my tangent line spot. And so it's always going to be the previous y, 1, plus my delta x, which is negative 0.3, and my slope, which is going to be 2. So this is 1 minus 0.6. So 1 minus 0.6 is going to be negative 0.4. No, I said that. It's not negative. It's positive. Sorry. 1 minus 0.6 is 0.4. Now I need to find my slope with my new ordered pair. My new ordered pair is negative 0.3, 0.4. So negative 0.3 plus 2 times 0.4. So this is negative 0.3 plus 0.8. And so that's going to be a positive 0.5. And so now I am at my last step. I am almost there. So in order to find our y value, remember, you want to keep your table nice and labeled. So that's going to be a y sub 1 plus your m times your x minus x sub 1. And remember, this was our delta x. So if you want to put a delta x there, it's fine as well. It's going to be the very same thing. So the previous y value is 0.4 plus your slope that we found, which was 0.5, and our delta x, which is negative 0.3. So I end up with 4. This is 0.4 and minus 0.15. 0.4 minus 0.15. So we can think of that as 0.40 minus 0.15. And so that's going to leave us with 0.25. I wish I could work every one of these, but I really want to get to logistic models with you. But the nice thing about Euler's method is you're going to do the same thing over and over again. There's nothing special about number 5, so I'm hoping that you will get C when you try that. I would like for you to go with me to number 6. Number 6 is another tabular type problem, and you're going to work this one, and you're going to look for the answer 2. And if you get stuck, you're going to email me. It's on the front of this packet. It is also located where you sign up for this session. You can find my email there as well. When you work number 7, you're going to get 5 halves as an answer. And then number 8A, golly gracious, I didn't get to as much as I wanted to. 8A is going to be negative 23/4. And 8B, you're going to find out that K is negative 1/3. Gosh, I wish I had more time. This question actually is from part of the 2012 BC exam. In this question, this particular question, and that's been several years ago, questions change, of course, They're never the same. But in this particular question, they ask 4 different approximation types. In this, they ask for a tangent line, they ask for a midpoint Riemann sum, they ask for Euler's method, and a Taylor series approximation. The word approximation is a huge buzzword, and you need to make sure that you know all the different types of approximations. If I have more time, I will come back and work one of these. But right now, I would like to talk to you a little bit about logistic growth. Logistic growth is a type of exponential growth. It is a type of growth. No, it's not exponential, but it is a growth that models population often. And when we talk about logistic growth, this is the differential equation associated with logistic growth. So I have dp dt equals kp times L minus P. All right, notice on the bottom, this is my independent variable. In this case, it's time. In the numerator, it is my dependent variable. That is, in this case, population probably. There's nothing magic about P, but that's the one I used. And so this K is just a constant. And then I have population again, and then I introduce another variable, but hold on just a second. L minus P, notice my dependent variable P appeared 1, 2, 3 times. That is important that you notice that. It is with your constant, and it is with this L. This L is a limiting capacity. It is a maximum, what we would often refer to as the carrying capacity. A carrying capacity is how much an environment can take. All right, so when we talk about a population, at some point food and water runs out, and we can only support a certain number of species. Okay, exponential growth. We've talked about that since probably Algebra 1, Algebra 2. Now, logistic growth. You may have seen this in your biology classes. My students often understand what a carrying capacity is because my biology teacher rocks. So as we have a population, it grows. So we have just a few parents, and then we have lots more kids, and then lots more kids, and then way more kids, and then suddenly that population is going to slow down as the carrying capacity is reached. Okay. It is interesting to consider that our carrying capacity, that is going to be the L. All right, now, if I were to have another hour, we might take this, and it's a differential equation, and we could do separation of variables here, and then we could use partial fractions, and we could go through a great deal of fun little math, and we would end up with our solution model here, okay? So you need to be most familiar with the differential equation that represents it. This is also something that you probably need to have some familiarity with, but you don't see this nearly as much as you will see it like this. And that'd be a fun activity for you if you ever want to find out how to get from the differential equation. It involves a partial fraction, and it's loads of fun. One thing I want you to notice right here, this is the graph of this population, and it is growing the fastest right here. Remember, growth is a rate of change. So I'm growing, and this is a rate of change. It's almost 0 here, and then it's positive. Notice it's always positive, but then it's really, really positive, and then it flattens back out. So our fastest growth is going to happen right here when the concavity changes. So we're concave up, and then we're concave down. So our fastest growth happens right there. And if it is a logistic model, that is going to be at L divided by 2. So whatever your limiting capacity or carrying capacity is, you're going to take that and divide it by 2. That will be your fastest growth. And they do ask that. So a couple of statements below this. It says limit of a population is always the carrying capacity L. This is also important. The initial population is not going to affect your carrying capacity. Your environment can handle a certain amount. And if you start at 20 and you are approaching your limiting capacity, if your carrying capacity is 200, it's still 200. If you start at 20 as your population, it's still going to level off at 200. If you start out at 2 as your population, it's still going to level off at 200. in a logistic model. Population is always growing the fastest when the population is half of the carrying capacity. That was what I just said right there. So I'm going to talk to you about the types of questions you might see. They are somewhat limited. They don't ask a great deal of things, but I want to pay attention to the ones that you may see. The number of moose in a national park is modeled by the function M that satisfies the logistic differential equation, and there you have it. Okay, so if you're looking at this, you're thinking, wait a minute, that doesn't look like what she just told me. That doesn't look like K times P times L minus P. You're right, it doesn't, but we might be able to make it look like that, where M is the time in years and M of 0 equals 50. Well, M of 0 equals 50, that's really nice, but that's almost to throw us off. It says, what is the limit as t approaches infinity of M of t? So I tell my students that you can't do anything with a problem until you know what you're supposed to do, till you know what they're asking for. So right there, the limit as t approaches infinity. So as time goes on and on and on and on and on, as time goes on and on and on, eventually this is going to, if it's logistic, and they told us it is, it's going to settle at our carrying capacity. So we are looking for a carrying capacity. I am going to tell you two ways to do this. And I will tell you that my students, half of them like one way and half of them like the other. So maybe you can latch on to one of these methods. One method that I want you to look at is actually a little more graphical. So when we look at this, our carrying capacity happens when the slope is 0. So our slope is 0 here, our slope is 0 here. So they've given me a slope. So method 1 that I'm going to talk about is going to happen. It tells us that our derivative would have to equal 0. All right, well, that's not too hard. I know that if this is factored already for me, then I know that we got 0.6 m equals 0, and that happens when m equals 0. Well, that's not going to be my, that's not going to be the time, at the situation at which we have a carrying capacity. And I also have 1 minus m divided by 200. So I could say m divided by 200 equals 1. So m equals 200, voila, you are done. Our carrying capacity happens when the derivative is 0. So if you set that equal to 0, that's when it happens. When our population is at 200, when our population is at 0. So we would know that this is the point at which we're starting, right here. And the other one would be our carrying capacity. So that's one method. That is not the most popular method, and that seems to not be the way that my students want to do this. We'll see how you like it. The other one, they want to make this differential equation, dm dt, equals 0.6 m times 1 minus m over 200. They want to make this look like the model that I gave them. And I think that's a great plan. So the way that you go about manipulating this is you're going to get a common denominator here. So that's 200 minus m divided by 200. And then, so this is the same thing as what we had here. If I factor out
You are frozen for me. Is anybody in the chat have Stephanie frozen as well, or is it just on my end? Okay, Stephanie, you're frozen. I'm not sure why. So Stephanie, if you can hear me, type in the chat that you know that you're frozen. Stephanie, can you hear me? I think she just got kicked off, so let's see if she can get back on. Aaron, do you have Stephanie's number?
Yeah, let me look for it. I think she probably will just log back on, but let me look for that for 1 second. Yeah.
Once she realizes she got kicked out. There she is. She's back.
Okay, so intermission is over.
You're back.
I'm so sorry. I had a power failure. I think we're back on now. I apologize. I don't know what happened there, but that made me panic big time. So here we go. I don't know what the last thing you heard me say because I was just talking away and then suddenly I was like, oh no.
I think what you have written up there, we got to where you stopped writing. So I think we probably got as far as you went.
So maybe you're caught up by now. All right, so we have a situation here where you're rewriting this. And we've got dm dt equals, now if I want to take this, I can factor out this 200. I've got 0.6 over 200 m, and you don't care what that equals, that's just a constant. And then I've got 200 minus m. So I have now made this look like a constant times my dependent variable. And then this is my carrying capacity minus my dependent variable. My students tend to like to manipulate this rather than think, okay? All right, so there is our first logistic model. Golly, that was embarrassing. All right, so let's look at question number 9. If you printed this prior to yesterday, you may have a different set of choices because I found a mistake. In my original one, I had A and B were the same, and so that's not good. It says, let K be a positive constant. Which of the following is a logistic differential equation? So this is just saying, do you know the model? All right, so I like this option because it looks like the differential equation is Kentucky. I'm from Kentucky. So this one, I have my independent variable. And although that looks enticing, that's wrong. Here I have my my dependent variable appears 1, 2, but not a third time. So my option that I want to select is E. I am going to skip now to question number 12. Would you go with me, please? So this is question 12. It says, which of the following DEs for a population P could model the logistic growth shown in the figure above? All right. So these are also not in they're not set up in the way that we think that they should look in our minds, the way that they're introduced. We have a constant times the dependent variable, and then times the limiting capacity minus your dependent variable. But I noticed that every one of these appear to be able to be factored. If I look at my graph, I hope you can recognize that our carrying capacity is 200. That's when we hit our point of no more people, no more of a certain species of a population. All right. So I'm going to jump right in. I'm going to try A. So dp dt. And I'm going to try A because it has a 2 in it. And 2 makes me think of 200 more than 1. I don't know. I also am more inclined to pick anything besides E because there's subtraction signs and I feel better about that. So E doesn't look real enticing to me. So dp dt. So if I think about this, this is 2/10. I'm just going to write that because I like fractions better than decimals. I'm a weird bird. All right, so 2/10 minus, that would be 1/1000th p squared. All right, so I noticed that I could factor out a p, so that sounds really good to me. I also would like to be able to factor out a 1/1000th. So I'm going to try that. And it would be easier to factor out 1/1000th if this 2/10 were actually in thousandths. And I love zeros because I can just add them. I can add 2 zeros to the bottom and 2 zeros to the top. So now suddenly I'm going to factor out 1/1000th. And I'm going to factor out a p. So if I do that from the first term, I end up with 200 minus p. So I might have just gotten lucky, friends, because now it says dp dt equals a constant times my dependent variable times limiting capacity minus my dependent variable. So I know that this is a logistic model, and I know that my carrying capacity is 200. Ta-da! My answer is A. I kind of cheated because I knew what the answer was, but this one is not a great choice because it has a plus, and I'm not as inclined to like B or D because it doesn't have the 2 in it. So I thought A and C were the most exciting, and I was right in this case. All right, logistic growth. Let's look at number 13 with you or together now. It says a population is modeled by a function P that satisfies the logistic differential equation. And then it's got this thing. This is another form of it, actually. My students like to always make it look like the way that we started. K times P and our limiting capacity minus our P. That's what they want theirs to look like, and I'm fine with that. It says if P of 0 equals 3, what is this? Well, you need to know your definitions. The limit as T approaches infinity of a population, that's just my carrying capacity when we're talking about a logistic model. So we want to find our carrying capacity. So our carrying capacity of this is going to be something. And then it says if P of 0 equals 20, what is the carrying capacity? Do you remember what I said about a carrying capacity a minute ago? I said that it had to be the same regardless of your initial condition. This is just an initial condition. This is just an initial condition. So we can say that both carrying capacities are blank, and we got to find out what that blank is. So both of the answers for letter A are going to equal what we find here. So dp dt equals P divided by 5. My hair keeps getting in the way. And then we've got 12 minus P divided by 12. All I did was get a common denominator there. I'm going to factor out that 12. So dp dt equals P over 60 times 12 minus P. So P over 60 times 12 minus P, my carrying capacity is right there. It is 12. All right. So if you'll notice, the 12 is sneaky right here. And this is another form of a logistic model. And if you have 1 minus your dependent divided by this will always be your carrying capacity. But I've found that my students and myself too, I want to depend on one thing that I can count on every time. And my brain connects with, I'm looking for it 1, 2, 3 times, no fractions in this. That's the way my brain works. If you want to remember it this way, fantastic. It's correct. So both of our carrying capacities are 12 in this situation. I would have answered this one is 12. This one is 12, just to make sure that my reader knows, hey, the answer is 12. And now it says, if P of 0 equals 3, for what value of P is the population growing the fastest? My students were all over the map on this one when they saw this question. They're like, I don't know what that means. And so this is the idea that if you have a carrying capacity and it is logistic growth, the maximum growth rate is going to happen at exactly halfway between the start and the finish. So halfway between 0 and 12, you're going to take your limiting capacity or your carrying capacity, and you're going to divide that by 2. So 12 divided by 2 is 6. We are growing the fastest at 6. We don't have any units, so we're not going to make up any units. Logistic growth used to be something that I was scared of. I was scared of it because of going from the differential equation to the solution is a lengthy process. But if you know the basics of logistic growth, you will do great on your AP exam. Let's go to 14. And this seems like the simplest question in the world, but people flip out because there are so many words. So it says the number of fish in a lake is modeled by the function p that satisfies this differential equation, where t is the time in years. Which of the following could be a graph of y equals p of t? So this is popping up in my session titled Logistic Growth. So we know that it's logistic growth. It'll be easy to quickly pick this. But if you will notice on your AP exam, you're 3 hours and 15 minutes into, or 3 hours and 10 minutes into your test, and you got 5 minutes left and your brain is tired. This doesn't say, hey, this is logistic. You have to recognize this as it's a differential equation. And in a differential equation in our BC curriculum, NAB, you can separate, and that's about the only option we have in our curriculum. There's way more when you get to your college level classes, but this is a logistic model. So you know what a logistic model has to look like. Which one of these appears to be logistic? Well, this looks like a logarithmic growth in some way. This looks like exponential growth. These two have a curve to them, so I'm feeling pretty good about these two, except I remember that in the middle of this, I've got to, when I change from concave up to concave down, that's where my fastest rate of growth is going to be happening. And this changes from concave down to concave up. So that's actually the lower one. So this is going to be my logistic growth model. Again, it seems simple because we're in the section entitled Logistic Growth, but you would need to be able to recognize that. All right, guys and girls, we did not get to work question number 11. I was hoping to get back to that one, but I will show you one thing. If we were at 3-2, that if you were tracing this slope field, it would look something like this. It would live along the carrying capacity. And they also ask at 0.8, that would mean that your population is too high to be supported by your environment. So things would have to die off because carrying capacity is as much as can be supported. Down here at the bottom, this is going to combine some of the things we talked about with Euler's method with this dy dt, this logistic. When you solve B on your own, you're going to be looking for an answer of 105/16. My students were not very excited about when we looked at this problem. They didn't like that fraction, but that's the answer that you should get. I appreciate you for hanging out with me this morning. Again, I would have loved to have been in a classroom with you and gotten some feedback and gotten to work some problems, let you work them, and then we talk about them. But this just didn't lend itself to that as much. You are going to do great if you will work really, really hard between now and May. Again, I am available for your help. Please feel free to contact me. I'd be thrilled to hear from some of you. I saw that someone was from Wisconsin this morning. How great is that? Love that. So please make sure and work hard for your calculus teachers. Know that we're all doing our very best to make your experience the best that it can be. And I wish you the very best. Ms. Hill, do you have anything as closing remarks?
No, that's all. Just thank you, Stephanie. That was awesome. And if you notice in the chats, they are telling you did a great job. So good job.
Well, that's nice. Thanks. Appreciate that.
If anyone was here the last session for mine and you did not get an answer key that you asked for, I cannot post those because they are for test security reasons. So if you are here today and you were here the last time and you were wanting answers to some of the things I did in the January session, please email me as well, and I can send you anything from that. So, Aaron, do you have anything? If not, I think we're good.
No, thank you all so much for joining. We'll have a recording of today's session posted to the bit.ly/advky site within a couple of days. Our next session is on March 6th with Amy Cash, and we'll be covering all things parametrics, polars, and vectors. So I hope to see you all back then.